So, in this tutorial, we are going to be creating an orbit propagator. And essentially what an orbit propagator does is, given the initial position and velocity of an orbiting body, it propagates the orbit through time and allows us to visualize its trajectory. This is the bare minimum of what the proprietary software systems toolkit, or SDK, does. Obviously, a professional and industry used software has more things to account for, such as aerodynamic drag, radiation pressure, etc. But we are only going to be focusing on the effects of gravity and assuming an ideal trajectory. The stuff that we'll be covering are the derivation of the equations of motion. This is called a central body force problem. And we will be deriving and solving these equations using Newton's law of gravitation and Newton's second law of motion. Once we have our equations of motion, we will solve them using the methods described in the earlier videos. And finally, we'll be visualizing this data using the built-in MATLAB functions Comet3. And we will actually go a little further and try to add some graphics to give us a better idea of what's actually happening. So with that, let's start deriving the equations of motion. So the first thing that needs to be done is to define our system. So let's say we have our Earth, and we can assume it's a point. With all of its mass located at the center. This is the mass of the Earth. This is its center of mass right here. Next up, we have our orbiting body, which for our intents and purposes, we can say it's a satellite. The most important thing that we can do is define the position vector, right? We can assume that the Earth is the origin and the satellite is at some position vector r. To get a little bit into some of the Calc 3 material, multivariable calculus, we can say that our position vector is going to be some function of x, some function y, and some function z. And all of these will vary with time, right? Pretty straightforward. Furthermore, we can define the unit vector, which I will do it in purple. The unit vector, which will simply be the position vector divided by its magnitude, or where the magnitude of the vector is, simply we use the Pythagorean theorem, x squared, y squared, z squared, and square root that, and that is where that goes. So yeah, and the position vector is, say here, this has unit length. This has a unitary length of 1. Next up, we can define the force of gravity. So if you remember from physics, we defined the force of gravity as negative g Earth, right? Mass of the Earth, mass of the satellite, which we will just call m for now, divided by the distance squared. Now, an interesting thing to note is that force is a vector, which means our value must be a vector. And for those of you that know, this vector acts in the same direction as our position vector. This is what we mean by a central body problem. So, force of gravity acts this way. And so the vector at the end is simply the unit vector of our position. And this makes sense if you think about it, right? The force of gravity is defined by this magnitude, and it acts opposite the direction that we are looking, right? From here, we can simply do a little bit of special definitions, and we can derive our equations of motion. So let's do that. So for our equations of motion, let's start with Newton's second law. The sum of the forces, that's bad. The sum of the forces is equal to mass times acceleration, right? These are both vectors. Let's put in the expression for gravity, negative g, mass of the Earth, mass of the satellite over r squared times r hat. Now, as we defined earlier, r hat is just the r vector divided by the magnitude. And so what we can do is we can actually do a bit of a useful substitution, which is we can say that this is our r vector, and instead of raising it to the second power, we raise it to the third power. I highly recommend that you go back and check that this is the true statement, and we shall continue from here. And next up we have the mass of the satellite, right? Because we care about the satellite, not necessarily the Earth. And then we have our expressions for acceleration. So x double dot, y double dot, and z double dot. And these are all in Cartesian coordinates. A similar derivation can be done in spherical coordinates, but it's a little beyond me to do it. From here, we can immediately see that the masses cancel, right? The mass of the satellite and the mass of the satellite cancels on both sides. From here, we can continue derive. We have separated our equations in acceleration and position. So we have x double dot, y double dot, and z double dot, all as vectors, is equal to negative g mass of the Earth over r cubed, and it's a function of position. And these are the equations of motion. This is what we will be using. And if you've seen the last video, we know that we can actually apply reduction of order, right? And we can simplify this into a form that MATLAB will be able to read, which is equal to x dot is equal to some function of x and t. Obviously, there's no t variable, there's no time-dependent forces here, but it is important that we do account for the possibility. I will not be deriving the reduction of order here, but the principles from the last video, two videos ago, still apply exactly, and it's a fun exercise to do on your own. So we have our equations of motion. Now let us implement them in MATLAB. So I'll move this off screen and open up MATLAB. So let's start by defining our force. So let's do this function. Also, if you haven't noticed, I went back and saw the video and realized that this is actually I made it very small. The text was very small and very difficult to see, and I did not enjoy reading the text in my videos. So here I've made the text a little bigger. Hopefully that's better, and I will figure out at the end of this video. Alright, so to define our position vector, we're going to be using this variable x, but don't let that confuse you. This x is different from the x component of our position vector. X is just a general term here. So the way we'll define it is we'll say that the first value in here will represent x, second value will represent y, and the third value will represent z. And now, using the knowledge gathered from our previous, from 2 videos ago about reduction of order, what we can do is we can define x4 as the first derivative of x. And we can do likewise for the other components, right? We can define the derivative of x, y, and z, the x, y, and z velocities, you could say. And we also have some constants that we need to take care of. In the last video you saw, in the spring mass dampener video, you saw that I used m, k, and b separately. Here I will just use them together. So the two constants that we have are the mass of the Earth, and we have the gravitational constant, which we'll just call g. And these are the only two constants that we care about. So yeah. Next up, we have to define our equations of motion. So as you saw, we had to look at the magnitude of the position vector, and this is pretty straightforward, right? Square root of x1 squared plus x2 squared, plus x3 squared. If you're wondering why I'm leaving all these parentheses here, it's easier for me to read, and if I ever need to go back, it helps me make sure that I'm not missing anything. So this is the position magnitude, or magnitude of the position vector. Magnitude of the position vector. Okay. Then from here, we just have to copy our equations of motion. So let's define the dx term. So the derivative term here, right? So we're doing the derivative of x1, 2, 3, 4, 5, 6. So the derivative of this will be a little long, but I hope there's no confusion as to where I got these terms. The derivative of x1 is the derivative of x, which is the velocity of x. So this is x4. The derivative of y is the velocity in the y direction. The derivative of z is the velocity in the z direction. Okay. And now we have to define the force that is acting in each direction. So we will define the force as its own thing. So the force is equal, so the magnitude of the force will be C2, which is the gravitational constant. Or sorry, no, it'll be negative C2 times C1, right? This is the gravitational constant times the mass of the Earth. And this will be divided by, for now and you'll see why I'm doing this, R mag squared. Oops, I forgot a parentheses here. R mag squared. So let me just quickly pull up the whiteboard. So the way I'm defining this right now is actually closer to what we had up here, right? Where I will define this R vector as, you have the X component divided by R, the Y component divided by R, and the Z component divided by R, right? I have not factored this out. And this is purely my own preference. You can obviously you can use the cube term. It is there for you. However, I feel more comfortable doing this. So the force that we have is the derivative of velocity is acceleration, and the acceleration is equal to the force in the component of the force in that direction. So we have the X component, we have the Y component, and we have the Z component. And this is pretty straightforward, right? We have x1 is the component, x2 is the Y component, and x3 is the Z component. And we simply divide this by R mag, right? Pretty straightforward. R mag divided by R mag. Whoops. And finally, we would implement these down here, right? So R sub x, force in the RY direction, and the component of the force in the Z direction. And assuming I haven't made any mistakes, this should be right. As you can very easily see that this is quite literally exactly what we had before, right? We've simply applied the reduction of order, and I wrote it in a way that I can understand, or rather, a method that I prefer. Obviously, you're free to choose how you define the system. So, given that, we have defined the function that represents our slope, and now we can start creating our orbit propagator. So, let's begin. So, my force of habit says we have a start key and a stop key. Oops, display stop. And let's look to defining our parameters. So, first we have our constants. Obviously we define this as the C vector, right? We want to be consistent with how we do things. And as I mentioned before, C1 will be the mass of the Earth, and C2 will be the gravitational constant. So, let me quickly pull those up. I don't have them memorized. Okay. And just to confirm, C1 is the mass of the Earth. So, the mass of the Earth is 5.972 e to the 24th. This is the mass of Earth. And then we have the gravitational constant, which is 6.6741 e negative 21. Gravitational constant. All of these are in standard units, meters, kilograms, etc. I'll just label that here just in case. Right, it's good practice to have your code commented so that people can understand what you wrote. So kilogram -1, seconds -2. Yes. Okay. We also want to. Some other constants that we care about are things like the rotation of the radius of the Earth, right? So we have the radius of the Earth, which is 6.371 e to the 6th. Actually, you know what? I'm going to do myself a little favor. I'm going to define these on their own. So mass Earth is equal to this number, and the gravitational constant is equal to this. So G is equal to this. And we will define this as M underscore E and G. Okay, so some other constants that we'll define are things like our spacecraft's initial position and velocity. So I'm going to use a bit of a simple example. You can check this with elementary physics, but I will use an altitude of 5 e to the 5, and this is in meters. Altitude of satellite, let's say, and it's in meters. Okay, I'm just going to press tab to align these. There we go. And this should be good. Yeah, we've already defined this constant vector here. So we're going to call this setup. Okay. Now we also have to define our time step. So in here we can use a larger time step, right? Because we're dealing with systems that, a larger system, so we're permitted to use a larger time step. So in this case, the time step will be 1 second. And we will use our t start will be 0, and our t stop will be, let's say, 6,000 seconds, right? We want to be consistent. We want to use seconds everywhere if we're going to use them. From here, I almost forgot, we have to define our span. This will be from t start, dt, t stop. There we go. And once we have this set up, it's just a matter of solving our differential equation, right? Setting up our initial conditions and whatnot. So let me rename this. These are our time parameters. And we will also be defining our initial conditions. So initial conditions. Now remember, the way that we've defined our system is that the x vector holds all the information, right? It holds our position and velocity. And so this is the format that our program, our function here, is expecting to receive its data. So I'm not going to do anything special. I'm just going to say that the initial position in the x is 0. The position in the y will be the radius of the Earth plus the altitude. And the initial z will also be 0. So as you can imagine, let me pull up my graphic. Yes, there it is. So if you have if we have our Earth, we have our Earth, and we say this is the x direction, this is the y direction, and this is the z direction, we're saying that the satellite starts right here, right? Where this is the radius of the Earth, this is the radius of the Earth, and this right here is the altitude, right? That's where we're starting. And if you use the formula for centripetal acceleration, you can figure out what this initial velocity has to be for this to be a perfect circle. And that's exactly what we're going to do here. So for our initial velocity, we're going to say it's going to be g times mass of the Earth divided by radius of the Earth, plus the altitude. And it's pretty straightforward where this came from, right? You can verify this for yourself. So from here, we expect to create a perfect trajectory right here, right? We expect it to be a perfect circle in the YZ plane, and we expect it to go in this direction, right? Pretty straightforward stuff. Obviously, these can be tweaked, and they don't even have to be in Cartesian, right? You can use the Keplerian orbit parameters, but for the sake of this tutorial, I will not be going into that. All right, so now we can start actually solving our thing. Constants. Yeah, there we go. Saved it. So let's actually solve the ODE. Let's give ourselves some ample space. More space. There we go. So let's do this. Well, from the Steve Brunton video I showed you guys, there's a neat trick we can use, which is we can set up an options thing. We can say ODE set, use relative tolerance, and set that to 1e to the -10. And we can have an absolute tolerance of 1e -10. We have to use 1s 1 to 6, just because we have 6 things in our position vector. If you're confused about what this is, to put it simply, it's the tolerance that the built-in ODE solver will try to adopt to, right? So now we have our ODE solver. We care about the time and the position that's solved from it. We have ODE 45, and we are feeding it in, and we are getting out the time and x data. And the name of this is one body. And we're feeding it in the time, the x, and the c, right? Time, x, and c. And we have to account for the time span. So time span, and the initial velocity position, which is this, and we're going to feed it our options. So this will tell it, when you solve this ODE, stay within these bounds. And as you can see, this is really small, so there should be virtually no error, right? It'll be very, very small, to the point where we shouldn't be able to see it. Okay, well, this will give us the data of in our x and y, and I guess now, you know what? We can just plot it right here. So solving ODE, and let's just quickly do a quick visualization. Visualization. For that, we're going to use the comet function. So comet3, and for those of you who are unfamiliar, comet3, the help button's right there for us. And we can see that it takes in, this is the way we want to look at it. If we want to display an animated comet through points x, I, y, and z, we just have to give it the data that it needs. So let's do that. Well, for our x data, we have x, all the rows in the first column. I'm sorry, no, all rows, first column. For the y data, we have all rows, second column. And for z data, we have all rows in the third column, right? And this makes sense. If we say that this is a column vector, the first column, or sorry, the first row, or sorry, first column will be x, y, and then z. And that's the data that we want to plot. Okay? So let's see here. Let's see if we can, all right, so it might be missing a closing parenthesis. Am I missing something here? Or is it just, oh, yes, you have to multiply, right? We are multiplying this. We're creating a ones matrix here. And I believe that's all the error that we have. So let's quickly run this code and see what value we get. So orbit prop. It's very likely I just misspelled something. Okay, looks like I misspelled something. So it's confused about t-stop. Okay, yeah, there we go, see. Hi. Alright, attempt number 2. Oh, there we go. So we have a very short-lived comet. Oh, there it goes. So it did trace out a path, although it seems like that path is a hyperbolic orbit, which means our comet actually escaped, which is a bit interesting, but we can see that it is working, right? Now, let's see. Let me see if I can figure out why this error happened. If anything, it would have to be around here. This would be where I made my mistake. Or maybe up here. Ah, yes. Gravitational constant is not to the -21st, it's to the -11th. To those of you who caught that early in the video, good job. To those of you who didn't, now you know not to trust me. Let's try this again. Okay, well, we got a bit stronger of a hyperbolic orbit, which shot off to the side again. However, that is more reasonable, I could say, than something where it doesn't. Let me continue. Let's continue debugging. So radius of the Earth is this number to the 6th power. This is in meters, right? So radius of the Earth, it should be in meters. Mass of the Earth is 5.9 something, 10 to the 24th, 10 to the negative 11th, 5 times 10 to the 5. All these should be right, per se. But I guess somewhere in here I messed up. Okay, so after painstaking efforts, that's the typo. I put x back into itself instead of the constant. That was my error, and that's why I was shooting off to infinity. Apparently, like, I'm not going to reason through it again. This was a nightmare to do. You don't need to do anything. Just don't make typos like that. Man, that sucks. I could have had this on the first try. Instead, I had to waste, like, what, 15 minutes trying to figure this out? Alright. Now, we get our propagator. It looks a little weird. We can fix that real quick. That's just the time stop. Let's just make it 24,000 seconds, right? And now if we propagate the orbit, you see, okay, it's going around, right? The Earth's at the origin, 0, 0, and 0. And it's going to make 2 whole orbits, right? If 6,000 made half an orbit, 2,400 should make 2. And this makes sense. Okay, then. There we go. So now we have our orbit propagator, and we know it works, right? We've tested it with the comet function. So, well, to be honest, that is the orbit propagator. That is all the physics and all the derivations that you need to create your own. Now, that being said, we can go to a greater length. We can implement some stuff that is more interesting. So, for example, as you may have noticed, when we actually run it, we just have a white background and some yellow comet following around in it. Obviously, that's kind of boring. It's useful for testing concepts, but if you want to create something that's a little more visually appealing, we have to add an Earth in there, right? And I can't take credit for this. This isn't my job. But if we search up MATLAB Earth plot, we can see that there's been quite a bit of work. Let me see if plot Earth 3D. Yeah, we can see there's multiple examples. I believe this is the one I used by Ryan Gray. Whoever you are, Ryan Gray, thank you very much for this. I'm very thankful that you wrote this code for me. But more or less what it does is you can change the color of the figure to black, and then through all this code that I don't quite understand, you can put a globe in there and have your orbit propagate on that globe. Now, unfortunately, I don't have it in me I don't have the confidence that I will be able to copy it exactly. However, what I can do is go to a previous piece of code I wrote. This is the orbit propagator I wrote like several months ago, actually. And it has all of his code implemented, so once again, thank you, Mr. Ryan Gray. And if we were to run this orbit propagator, let's see if it goes. Yep. We can see that it plots the Earth and the orbit on top of it. So yeah, that is the visualization tools that you can use. I was going to cover this, but I don't trust myself to do it. The code is very readable. He left plenty of comments and some other stuff, as well as some pretty good explanation. He gave us the image file as well. So thank you once again, and definitely look into implementing this. I have shown you guys how to make the bare bones propagator. Definitely look into him for the visualization tools. And with that, we have wrapped up another tutorial. Thank you for watching, and good luck creating your own.